Stop guessing if a prediction is safe to trust. Add uncertainty with guarantees in minutes. You will learn a practical way to attach calibrated, trustworthy uncertainty to any regression model so you can make safer decisions. I'm Professor Pi, teaching AI foundations with simple Python. Conformal prediction helps when a point estimate is not enough. Imagine a model that tells you a single temperature number. Now, imagine you get a range that says how uncertain that number is. That extra information changes how you act. Conformal prediction is a family of tools that turn residuals from a model into honest prediction intervals. Practitioners reach for it when they need statistical guarantees without reworking their whole pipeline. At a high level, the idea is simple. Train any regression model. Use held-out data to measure how far predictions miss true values. Turn those errors into a rule that expands future predictions into intervals. Strengths are that intervals are distribution-free and easy to compute. Weaknesses are that they rely on the calibration data being representative. We will build a tiny toy with a linear regressor wrapped by MAPIE to show how intervals form, how calibration works, and how alpha controls the trade-off between width and coverage. The code is short and uses plain lists for features so you can map it to real datasets easily. This snippet builds a simple linear model wrapped by MAPIE to get a valid prediction interval. The list X holds one-dimensional features and Y holds targets with slight noise. The object MapieRegressor, with method set to naive, learns residual dispersion from the training data to calibrate uncertainty. The call predict on the new input returns a point prediction P and an array pi containing lower and upper bounds for the chosen alpha. The alpha value of 0.1 targets 90% coverage, so intervals should be reasonably wide. The printed width shows how much uncertainty the model reports around that single prediction. Now we will split data to separate training and calibration and show coverage. This example splits the toy data into a small training chunk and a calibration chunk to show conformal calibration. The estimator est fits a plain linear regression only on the training portion. The MapieRegressor with CV set to prefit then uses xcal and ycal to compute residual quantiles without refitting the base model. The call predict on xcal returns calibrated intervals, and the loop computes the fraction of calibration targets that fall within those bounds. Increasing alpha reduces the target coverage and narrows intervals, while decreasing alpha increases coverage and widens intervals. The printed calibration coverage indicates how well intervals match the desired rate. Next, we contrast two MAPIE strategies to see precision differences. This code contrasts two MAPIE strategies to reveal a practical trade-off. The variable MA wraps linear regression with the naive method that uses a single residual quantile, while MB applies CV plus to aggregate cross-validated residuals for tighter, more robust intervals. Both predictors call predict on the same x0 with alpha at 0.1 to ensure a fair comparison. The variables WA and WB compute the respective interval widths, and the choice best reports which method is narrower while targeting similar coverage. If your data are moderately sized, CV plus often yields sharper intervals than naive. The printed winner shows which approach is more precise here. Now we will show how alpha changes the interval size directly. This snippet demonstrates how the alpha parameter in MAPIE directly trades coverage for interval width using the CV plus model MB from earlier. Two predict calls compute intervals at alpha values A1 and A2. The variable W1 measures the 90% interval width, and W2 measures the 80% interval width on the same input. The ratio shrink quantifies how much the interval tightens when coverage decreases. Raising alpha narrows intervals and can improve downstream decision precision, but risks missing more true values. Lowering alpha does the opposite. The printed width ratio makes the trade-off concrete for choosing an operational threshold. Next, we run a tiny test on unseen points to estimate empirical coverage. This example finishes with a tiny but complete baseline that evaluates uncertainty on new points. The list XTE holds unseen features, and YTE stores their targets. The CV plus model MB calls predict to produce 90% intervals for each test point, and the loop computes how many targets land inside those bounds. This yields an empirical coverage estimate on fresh data, which should be near the intended level, but will vary with sample size. If you reduce alpha, expect higher test coverage but broader intervals. The printed test coverage confirms whether you can trust these intervals in simple deployment. This toy maps directly to a prototype service. Replace the list inputs with a production feature matrix. Keep your trained base model and use a held-out calibration set that matches incoming traffic to maintain honest uncertainty estimates. Recap: conformal prediction wraps any regressor to produce calibrated prediction intervals. Use it when you need guaranteed coverage without strong distributional assumptions. Caveat: intervals depend on calibration data being representative, and sample size affects variability. Next step: tune the alpha parameter to find the best operational trade-off between interval width and target coverage for your application. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.